Let's compute the curl and divergence of various two-dimensional vector fields. I've included images of the vector fields. They're not great, but like in this first one, you can see that the vectors are sort of all pointed outwards from the origin, and as you move away from the origin, they get longer. And if you look at the definition of the field, that confirms that geometry. Okay, so these are all 2D vector fields, so we're going to use the two-dimensional sort of formulas for curl and divergence, the ones that appear in Green's theorem. So curl, remember, is partial n, partial x, minus partial m, partial y, and then divergence is partial m x plus n y, like this. Okay, so if this is the vector field f, and c here is just understood to be some scalar, some constant, then the curl of f is apparently 0 plus 0. See that? The partial of the n component with respect to x is 0 because there aren't any x's in there. And the partial of the m with respect to y is 0 as well. And if you look at the picture, that's sort of reasonable, right? I don't see any spiraling happen, any whirlpools happening. So the curl at any point in this vector field apparently is 0. Okay, for divergence. Okay, so for the divergence here, if you go to any point in this vector field, the tendency of the vector field to sort of escape the point or diverge from the point is 2c. So that's consistent across the entire plane. And interpreting this is a little bit subtle, but if you think about it, you can see the sort of the discrepancy between the lengths of the vectors just to like right here to the left and the right of the point. The vectors are slightly smaller coming into the point on the right, and they're slightly larger going away from the point on the left. And so there is a net like outward flow from each point in this vector field is kind of what we're getting from this divergence computation. Okay, how about for this shear field here? Let's call this vector field G. The curl is the partial derivative of the n component function with respect to x is 0, minus the m component function with respect to y is 1. So we're getting negative 1 as the curl. And I can, again, the picture is a little bit difficult, but let me describe the vectors here. So what we have are all horizontal vectors, and they're a little bit longer as you go away from the x-axis. And since the x component is equal to the y component of the point, up here, the vectors are pointed to the right, and down here, they're pointed to the left. So if you're standing at any point on the plane, then, for example, right here, the flow is to the right above this point. And the flow is also to the right below the point, but it's a little bit less of a flow, right? It's a little bit faster up here than it is down here because these vectors are longer. So that's going to cause rotation like this, because of the sort of discrepancy in the speeds of flow above and below. It's going to cause some spiraling around the points. And that's why we're getting a negative 1 because counterclockwise rotation is considered negative. Okay. Now down to here, we definitely have some rotation here, right? So if you can understand this image, I'm seeing a counterclockwise rotation. As you go away from the origin, the speed of rotation is faster, but we're just seeing this consistent circling around the origin. Let's compute divergence. Oh, did I do it? I forgot to do it. Sorry. Let's go back up here. I apologize. Let's do the divergence of G. Divergence of G is the partial of m with respect to x plus partial n with respect to y, and that gives us 0. And if you look at any single point in this vector field, there's as much like of arrows coming in as there are coming out. Like if you look just to the left of this point, there's an arrow coming in, but it's the exact same length as the arrow going out. So the divergence here would be 0. Okay, now back to the rotation field. All right, so I do expect to get some curl here. Let's call this one FGH. So the curl of H is going to be partial n with respect to x, which is c, minus partial m with respect to y, so that's a negative c. So for curl, we're getting 2c. And that positive, well, okay, if c is a positive constant, which would match the drawing that I have here, then we're getting positive curl, which is clockwise rotation. So that sort of makes sense. And then let's do divergence. This is partial m with respect to x plus partial n with respect to y. And we're getting zero divergence. So there is as much sort of flowing in as flowing out in this vector field. Okay, here's another whirlpool, but you can see that, so let's call this maybe capital I. It's just the previous vector field, but it's been scaled a little bit. We divide the vector field negative yx by its magnitude. And so what this is doing is it's creating a vector field that has all unit length vectors, but it's still spinning around because of the arrangement of the negative y and x. So I'm going to do partial n with respect to x. And then I have to do partial m with respect to y. So what is going on here with this zero curl? Curl is rotation, right? How are we getting zero curl for this clearly spinning vector field? Well, this is what's happening. Look at the vector field and where it's spinning. Right at the origin, I see rotation around the origin, right? But this vector field is not defined at the origin. So I couldn't sort of associate any sort of measurement of curl at the origin because that's not in the domain of the vector field, right? Now, if I look anywhere else in the vector field, let's focus right here or something. I'm asking myself, is there rotation around this point? And in order to understand that, one way to look at it is to look at the flow right above the point versus the flow below the point. As we saw with the shear vector field, if there's faster flow above than there is below, then you're going to get clockwise rotation. But here, since we have all unit flow, the flow above it is exactly the same as the flow below it. So you're actually just getting this nice consistent rightward flow at this point. There's no spinning around that point. And this is true for all points in the plane. You don't have rotation around any point because the flow is simply consistent around it. And that's unlike what was happening here. So the origin is not unique here. Like the origin, you have flow in the counterclockwise direction for this vector field H, but you also have it over here. And it's because as you move outwards, the vectors are getting longer. So to the right, for example, of this point, to the right of this point, you've got longer vectors. To the left of it, you got shorter vectors, so that creates a counterclockwise spiral around that point. Okay, let's do divergence of I. You might want to think about what you expect out of divergence even before you compute it. So I need to do partial of m with respect to x. Okay, after computing the partial derivatives, I see that dm dx is the opposite of dn dy, and when you add them together, you get 0. So I'm getting no divergence anywhere, and it's sort of for the same reason. You've got unit flow coming into the point, and you have unit flow going out of the point. So there's no net divergence away from the point or into the point. Okay, let's practice computing divergence of a three-dimensional vector field. Okay, so I'm just emphasizing here that when you compute either curl or divergence of a three-dimensional vector field, you're going to want to use the dot or cross formulation of divergence and curl when you do that. So there you go. Just keep in mind that divergence is a scalar expression, whereas curl is a vector expression in that case. All right, let's do a little bit of theory now. When we combine the operations involving the del operator, like computing a gradient versus computing the curl of a vector field, or the divergence of a vector field. So for example, let's take a look at the situation where we might have like a 3-variable function g. We compute the gradient vector field of g, and then we compute the curl of that gradient vector field. Let's see what happens. Okay, what is the gradient of the function g? Well, it's g sub x, g sub y, g sub z, right? Partial of g with respect to x, with respect to y, and with respect to z. All right, how do I compute a cross product? Build my matrix. Okay, so I'm going to fill this out. I'm taking the partial derivative of gz with respect to y. That's how this combination is interpreted. So I could write that as g sub zy, right? Partial derivative of gz with respect to y. Okay, I'll continue. Okay, look at the result here. I've got in each of the components of the curl computation, I've got mixed partial derivatives of g, so gzy and gyz. Well, if the g function happens to have continuous second partial derivatives, then by Chloros theorem, I know each of these mixed partials are equal to each other. So gzy is actually equal to gyz. So this is 0, this is 0, and this is 0. So what this is saying is if you have a vector function with, gotta be careful here, a vector function with continuous second partial derivatives, which is usually the case in the vector fields that we study, then the curl of the gradient field is going to be 0. So that's what I have here in the statement of the theorem. The curl of the gradient field is 0, and it turns out that this other computation I'm going to do, the divergence of the curl of a vector field, are both 0. So let's verify that right here. So start with a vector field f, compute its curl, and then compute its divergence. Okay, so the curl is, okay, if you write it all out, the cross product gives you this for the curl, and now I'm going to dot with divergence. So I'm doing this dot product. So when I take this dot product, I'm putting partial with respect to x next to this expression here. So taking the partial derivative of py and nz with respect to x results in these partials. And then I add on to that the derivative of this expression with respect to y. And then finally, okay, and as before, if my component functions have continuous second partial derivatives, then things cancel. So for example, mzy is the same thing as myz, so these two terms cancel. And same with the p's and the n's, so I just get a big fat 0. Here, 0 is a scalar quantity, not a vector quantity. I'm asking about a divergence. What's the divergence of the curl of a vector field? It's 0. Okay, lastly, talking about sort of combining these types of operations, if you start with the gradient of a vector field and then you compute the divergence of that gradient, so that's above we did the curl of a gradient vector field and we got 0. But if you compute the divergence of a gradient vector field, you don't normally get 0, and we combine the two del's in this situation and write it like this. This is called the Laplacian of a function, and it's an important operator, and if you end up getting that the Laplacian of a function is 0, it's a special type of function. It's called a harmonic function, and these things are studied in areas of mathematics and science.